Welcome to homework.
So for this question, we are going to be using this balanced chemical equation to help us solve this problem. For the first part of this question, they are asking us how many liters of ammonia we need per liter of flue gas. So some notes that they give us to help us figure this out is the partial pressure of nitric oxide. So they tell us that the partial pressure of nitric oxide is equal to 4.5 times 10 to the negative fifth atmospheres. They tell us that the pressure for the reaction is equal to 1 atmosphere, and they tell us that the temperature is equal to 365 degrees Celsius. I'm just going to add 273 Kelvin to this, so our temperature is going to be 638 Kelvin. So they want this in volume of flue gas is equal to 1 liter. So for part A of this question, we need to figure out how many moles of ammonia we have. So to do that, we first need to calculate the moles of nitric oxide. So moles of nitric oxide. For this part of the question, we're going to be using PV is equal to nRT. So we're looking for moles. So N is equal to PV over RT. So our number of moles of nitric oxide is equal to 4.5 times 10 to the negative fifth atmospheres. We're going to times that by our volume of flue gas that we have, which is 1 liter. And we're going to divide that by our R value. For R, we're going to be using R is equal to 0.0821 liters atmosphere per mole Kelvin. And we're going to times this by our temperature, which is 638 Kelvin. So our moles of nitric oxide is going to be 8.6 times 10 to the negative 7th moles of nitric oxide. And this is per liter flue gas. Alright, so now that we have our moles of nitric oxide, we can calculate our moles of ammonia. So if we go back up here to our balanced chemical equation, we'll see that we have 4 moles of nitric oxide to every 4 moles of ammonia. So to get the moles of ammonia, we're going to take our moles of nitric oxide, so 8.6 times 10 to the negative fifth mole nitric oxide, and we're going to times that by 4 moles ammonia and divide that by 4 moles nitric oxide to get the moles of ammonia that we have. So moles of ammonia is going to be 8.6 times 10 to the negative 7th moles. Alright, so now that we have the moles of ammonia, we can get the volume. So volume of ammonia is going to equal nRT over the pressure. So V is going to equal our number of moles that we just calculated, so 8.6 times 10 to the negative 7th moles. We're going to times that by the same R value, 0.0821 liters atmosphere per mole Kelvin. We're going to times that by the temperature, which is 638 Kelvin, and divide that by 1 atmosphere. So our volume is equal to 4.5 times 10 to the negative fifth liters of ammonia per liter of flue gas. Alright, and that is how we solve the first part of this problem. The second part of this problem is asking us our mass, or how many grams of ammonia are needed per kiloliter of flue gas. So they tell us that the pressure for this reaction is still 1 atmosphere, and our temperature is still equal to 638 Kelvin, and the volume that we have of flue gas is 1 kiloliter. So 1 kiloliter is equal to 1,000 liters. Alright, so we're just going to use the same process. So we want to find the moles of nitric oxide that we have. So we know the partial pressure, so 4.5 times 10 to the negative 5th atmospheres. We're just going to times that by the volume of the flue gas, so 1,000 liters. Divide this by 0.0821 liters atmosphere per mole Kelvin, and times that by our temperature, so 638 Kelvin. So our moles nitric oxide is equal to 8.6 times 10 to the negative 4 moles nitric oxide per kiloliter of flue gas. Alright, so now that we have the moles of nitric oxide, we can find the moles of our ammonium or ammonia. So moles ammonia is equal to our moles of nitric oxide, so 8.6 times 10 to the negative 4 moles nitric oxide, and we know our molar ratio is 4 to 4, so for 4 moles ammonia, we have 4 moles of nitric oxide. So our moles of ammonia is equal to 8.6 times 10 to the negative 4th moles of ammonia. So then to get the mass of ammonia that we need per kiloliter, we know that the molar mass of ammonia is 17.03 grams per mole. So we are just going to take our moles of ammonia and we are going to times that by its molar mass. So our answer is going to be 0.0146 grams of ammonia per kiloliter flue gas. Alright, and that is how we solve the second part of this problem.